Today I'm going to be working out a homework solution to question 4.21 from the Top Hat homework, which is using the following equation, determine the percent yield from the following reaction if 3.025 times 10 to the first grams of octane reacts with excess oxygen to produce 8.195 times 10 to the first grams of carbon dioxide. So from the question, we know that we're going to be needing to do percent yield. And the percent yield equation is just actual yield, which is how much did we really make, over theoretical yield, which is how much would we have made in a perfect world. And that's all going to be multiplied by 100 because we want to be talking about things in terms of percents. So in terms of variables, we need to solve for actual yield and we need to solve for theoretical yield. But one of those things has been given to us in the question, and that's right here where it says we've produced 8.195 times 10 to the first grams of carbon dioxide. Now I think it's a little bit easier if we just go ahead and write that as 81.95 because that's not already a huge number. And that is our actual yield, or how much carbon dioxide did we actually make. So we can go ahead and erase that and just plug the 81.95 grams up in its place. So we're already halfway done with the question. What we have to solve for next is the theoretical yield. So to solve for theoretical yield, we want to know how many grams of octane did we have at the beginning, and let's say everything went perfectly, how many grams of carbon dioxide would we have at the end? So let's take what we already know, which is going to be that we started with this amount of octane. Just like I did before, I'm just going to go ahead and rewrite that as 30.25 grams. So here we go. We're going to start with 30.25 grams of octane, which is C8H18, keeping in mind that the ultimate goal is to go into grams of CO2. Now, the only way that we can relate these two things is through their molar quantities, and that's when this balanced equation that they gave us is really going to come in handy, because then we know how many moles of octane relate to how many moles of carbon dioxide. So first thing, let's go ahead and get our grams of octane into moles of octane. And to go from grams to moles, we're just going to go ahead and use the molecular weight. So that's 114.23 grams per mole of C8H18. Go ahead and put that down there too. So if we just stopped right here, we'd have that in terms of moles of octane. So now what we can do is go ahead and say how many moles of octane are in how many moles of CO2. And that's when we're going to look up here and say for every 2 moles of octane, we make 16 moles of CO2. Stopping right here, we would have a final answer in terms of moles of CO2. So we're very close. What we really want is grams of CO2. So just like in the first step, to go from moles to grams, we're going to use the molecular weight. So the molecular weight of carbon dioxide is 44.01. So let's go ahead and get that here. So 44.01 grams of CO2 per 1 mole of CO2. So before I go ahead and give you the actual number, I just want to go through and make a note about how this dimensional analysis worked. So we started with grams of octane, and then we got rid of that here. Okay, so what we're left with is moles of octane. But then we got rid of moles of octane, leaving us with moles of CO2. Got rid of moles of CO2, leaving us with grams of CO2, which is what we actually wanted. So going ahead and doing that math, what we get at the end is 93.23662786 grams of CO2. Now I know that's a big number, but we don't want to round until the very end, so that way we can make sure that we have the correct numbers of significant figures and that we are as accurate as we can possibly be. So going back to our percent yield equation, we already have this top number, which is 81.95 grams from our actual yield. You'll remember that just came from right, ooh, that's not very helpful. That came from right here. And now we have solved for our theoretical yield on the slide before, which was 93.23662786. but we can go ahead and multiply that, divide them, and then multiply by 100, which gives us 87.89464171%. So let's go back and look at significant figures so that we can get this number the right way for top half. So we started with two numbers in the equation. We had this 30.025, and that has four significant figures. So how many did the other have? And that's when we'll look here and see that this also has four significant figures. So our final answer, we want to have four significant figures, meaning that this big long number is going to transform nice and down into 87.89%. But if we look up at the top, you'll see that it does want us to have it in significant figures as well as scientific notation. So we're going to go ahead and just turn that back into scientific notation, which will give us 8.789 e to the positive 1.